Okay, welcome back. So, we have come up with a mathematical representation wherein our signal x of t is now expressed as a linear combination of harmonically related complex exponentials. I mean, I have a series of exponentials which are harmonically related in the sense कि उनका जो fundamental frequency है, they are related by a factor k. Fine, and I am getting a linear combination, summing them up, and in that way I am representing my input signal x of t. So you can see the parallelism between the analysis, yeah, for this matter, the representation here. If you go back to our LTA analysis that we did in the second chapter, वहाँ पे we had a similar kind of analysis. We started from this very point कि our signal x of t is expressed as a linear combination of shifted impulses, right? So there's a lot of similarity between the analysis. Just that this time we are expressing our signal x of t as a linear combination of harmonically related complex exponentials. So first what I did in the analysis, I first tried to mathematically put forth what do you mean by harmonic relations. So it simply means that you have exponential, इसका कुछ time period है, same time period will be for this exponential, wherein I have introduced the parameter k in the exponential. And then the second relation will be with respect to the fundamental period or the fundamental frequency, wherein the fundamental frequency of these signals, these exponentials, they will be related again by a parameter k. Okay. Now let's call it, okay, we were numbering the equations, so we have reached to 3. Let's call it equation 4. Right? So this is, by the way, known as the Fourier series representation. So this is our Fourier series representation, k running from minus infinity to plus infinity. A of k is just the coefficient e raised power j k omega naught t. Alternately आप ऐसे भी लिख सकते हैं k is equivalent to minus infinity to plus infinity. You can also express it in terms of the time period capital T. So omega naught के बदले 2 pi by t, and then the t. Please remember, there's a property that if you come up with a signal which is the sum of the periodic signals, the signal itself will also be periodic. So x of t is periodic because we are expressing it as a summation of periodic exponentials. So it will also have a period, not the fundamental period. It will have a period t. Okay? Now, in this equation, we have, if we take k is equivalent to 0, fine. So you will see x of t is equivalent to summation k running from minus infinity to plus infinity a of 0, then e raised power 0, which is actually equivalent to k is equivalent to minus infinity to plus infinity a of 0, which is simply a of 0. Okay. So for k is equivalent to 0, equation 5, x of t, it becomes a constant having a value a0. Then again, if you take k is equivalent to plus minus 1, you will have x of t, k running from minus 1 to plus 1, a k e, then we will have the exponential e raised power, it will be plus minus j omega naught t. We're basically interested in this. So in this case, that's for k is equal to plus 1, yeah, k is equal to minus 1, you will have a exponential there where the fundamental frequency is because we have only the parameter omega naught in the exponential. Fine. So in this case, इस केस में constant था, इस केस में it will again be exponential with the fundamental frequency omega naught. Fine. Then again, if you take k is equal to plus minus 2, you will have an exponential x of t where in the summation will run from minus 2 to plus 2. We're not interested in the summation. We're basically interested in what kind of exponential we'll have. So this will again be exponential, but this time around the fundamental frequency, so corresponding to this, okay, yeah, let me just, so fundamental frequency first term with this, it will be twice omega naught, right? So a0, it is a constant term corresponding to k is equal to plus minus 1. We have what's known as the first harmonic, right, with the fundamental frequency omega naught. For k is equal to plus minus 2, we will have what's known as the second harmonic. Similarly, you can keep on giving the values. For a typical case, plus minus n, you will have a signal x of t summation k running from minus n to plus n, a of k e raised power plus minus n j omega naught t. So this will be the nth harmonic. अब इन हार्मोनिक कंपोनेंट्स में क्या फ़र्क है? It is basically the fundamental period or the fundamental frequency. ठीक है? So what we have done here is we have expressed our signal x of t in terms of complex exponentials which are related harmonic, and you can see this is the relation. Iska omega naught, iska twice omega naught, 3 omega naught. So all these individual exponential components, they are related harmonically. Okay, so we have expressed our signal x of t as a linear combination of harmonically related complex exponentials, and this kind of relation, this kind of representation is known as the Fourier series representation. And when you expand this, you will have different harmonic components, different exponential components जिनकी अलग अलग fundamental frequency होगी. Overall जो signal x of t है, it has to be periodic with the period t, right? Now before we proceed further, we'll take a simple example just to get a better insight in this Fourier series. So we have an example here where we have a signal x of t, and it is continuous in time, as is evident from this representation, and it has a fundamental frequency that is omega naught is equivalent to, it is given 2 pi, right? And it is expressed in terms of this summation as a Fourier series, k running from minus 3 to plus 3, a of k e raised power j k 2 pi t, right? It is also given that a0 is 1, a1 is equivalent to a of minus 1 is equivalent to 1 by 4, a2 is equivalent to a of minus 2 is equivalent to 1 by 2, then a3 is equivalent to a of minus 3 is equivalent to 1 by 3. We need to kind of express it, expand it, this Fourier representation, and see what are the harmonics, right? So it is given that x of t is summation k running from minus 3 to plus 3, a of k e raised power j k 2 pi t. So if I expand this summation, I will have terms like a subscript minus 3 e raised power minus j 6 pi t. Then I will have a minus 2 e raised power minus j 4 pi t. Then a minus 1 e raised power minus j 2 pi t. Then a constant term corresponding to k is equal to 0. Then I will have terms like a1 e raised power j 2 pi t plus a2 e raised power j 4 pi t plus a3 e raised power j 6 pi t. Okay. I can do a bit of rearranging. I will first have the constant term a0. Then what I will do is, since a minus 1 is equivalent to a1 जो दिया गया है, so I will arrange these terms something like this, that a1, okay, I will just, let me add some steps, j2 pi t plus a minus 1 e raised power minus j 2 pi t. Fine. Then a2 e raised power j 4 pi t plus a minus 2 e raised power minus j 4 pi t. And then I will have a3 e raised power j 6 pi t and a minus 3 e raised power minus j 6 pi t. Now a0 is equivalent to 1, so I'll have 1 here. A1 is equivalent to a minus 1 is equal to 1 by 4, so I will have 1 by 4 and in brackets e j2 pi t plus e raised power minus j2 pi t इन दोनों के लिए. ठीक है. Similarly, a2 is equal to a minus 2 is equal to 1 by 2. So in दोनों के लिए 1 by 2 will be common, and internally I will have e j4 pi t like this. Then a3 is equivalent to 1 by 3, so I'll have 1 by 3 e raised power j 6 pi t plus e raised power minus j 6 pi t. Okay. Then I can use the Euler's relation where e raised power j theta plus e raised power minus j theta, चलिए मैं यहाँ पे लिख देता हूँ that twice cos theta is equivalent to e raised power j theta plus e raised power minus j theta. Okay. So what will this become? 1 plus 1 by 4 twice cos 2 pi t, then plus 1 by 2 twice cos 4 pi t plus 1 by 3 twice cos 6 pi t. Then it will be 1 plus 1 by 2 cos 2 pi t. Then what? Okay, it will be simply cos 4 pi t, then 2 by 3 cos 6 pi t. Okay. Now first term, this is the constant term, this is my first harmonic, second harmonic and third harmonic. So in totality we have 3 harmonics here and a constant term. Okay. And your signal x of t is expressed as a summation of these. I will try to see graphically what actually we mean by this. So I will just try to plot each of these harmonics, so that will give a better insight. So first we have a constant term. The constant term to Bahral, it is a simple term, so it will be simply like this. It's a constant term throughout, इसका value 1 है. Fine. So this is, let's call it x0t. It is simply equivalent to 1. So with respect to time t, it will have a constant value 1. Then the second signal is your pure cosine signal. लेकिन इसका जो amplitude है, it is scaled by 1 by 2. So it will be something like this. It will be, I'll just try to make it. Let me use, okay, red is fine. इसका value 1 by 2 होगा, so it will start from, I have to slightly make it larger. Okay, it has to be curved, can't use a straight line. Let me see. Anyways, I will just draw it using this. So it will be like this. We have to draw one period, so something like this, and here. Fine. This is one period, then it will repeat. You can also go to the negative axis. It will be something like this. And important point, let's first call it x1t. So this is 1 by 2 cos 2 pi t, and ये जो ये यहाँ पे value है, it is 1 by 2. The peak, it peaks at 1 by 2. Then we have cos 4 pi t, so it will again be a cosine signal, just that इसका जो frequency होगा, it will be twice that of x1t. Now I'll try to plot it. Just a second. तो इसका amplitude थोड़ा, because it is 1 by 2, इसमें scaling factor नहीं है, so it will have a higher amplitude. And I will just try to drop some projections. I'll try to make it a bit, so here, so one cycle of this signal was from here to here. तो क्योंकि frequency double होने वाली है, तो I will have how should I, so half is where, somewhere here, so इसमें I should be able to accommodate, so something like this, then it will continue. Okay, then again you can proceed on the negative axis. Fine. So the difference is, so okay, this is 1 and this is cos 4 pi t. Let's call it x2t. Fine. So similarly, you will have the third component 2 by 3 cos 6 pi t, which will have a higher frequency. So this amplitude will be 2 by 3, which means less than, slightly less than, so it will have a higher frequency. Obviously it won't be perceivable here, so it will be something like this, a higher frequency cosine signal. Okay, and it will peak at 2 by 3. So let's call this x3t 2 by 3 cos of 6 by t. So as we mentioned mathematically previously in the general representation, कि जो individual components होंगे इस representation में, they will be harmonically related. Now we have taken a typical example here where our values are defined. We have done a bit of mathematical analysis and we have come up, these are the constituent terms that are in which this signal x of t is expressed. We have a constant term, this, we have a first harmonic, this, we have a second harmonic which has twice the frequency than the first, twice the fundamental frequency. Then obviously scaled by amplitude, this will be scaled by 1 by 2. इसमें scaling factor नहीं है, so 1, so इसमें scaling factor 2 by 3 है here, and again it has a frequency which is 3 times the first component here, like this. Fine. And overall जो आपका signal होगा, it will be basically sum of these three. So जो, obviously I can't draw it exactly, but it is basically a sum of these two. So it will have a, it will be something, I mean sum of these three, so something like this. Okay, again I'm going here, something like this, then it will drop down, then a higher perk. Fine. Overall signal भी periodic होगा with the period t, and these are the individual components which are, please remember, these are harmonically related. Harmonically in the sense कि इनका जो fundamental period है या fundamental frequency है, they are related to each other through a scaling factor k. Okay, so this was a typical example that tells you that whenever we express our signals in terms of these Fourier series, they will have individual components. Like in this case we had 4 components. First one was a constant component, then we had 3 more components which were sinusoidal in nature, and unki frequencies, they were related. So in other words, they were harmonically related. So this is a typical Fourier series representation. We'll stop here and we'll continue with this general analysis in the next videos, where we'll be interested how to get these coefficients a of k. Okay, we'll stop here. Next video will be further doing the deliberations, and we'll be trying to see how to get these coefficients.